thanks. Yes. Thank you. Okay.
So this, because you fixed gauge and fixed, I mean, there's not a lot of symmetry in terms of time here. So explicit time dependent and D00 sticks out explicitly.
Exactly.
So this is can you say this is the most general action consistent with spatial diffeomorphism?
Yeah, time dependent spatial diffeomorphism. So this is the
spatial diffeomorphism.
Yeah, from 4D diffs broken to. Now, I don't know the symbols of this thing. Time dependent, space diffs.
Very good. Okay.
So instead of SU3 goes to U1, is this.
Okay.
No, thanks. And time dependent is important. For example, GII is not invariant because of the time dependence. So the extrinsic curvature we have to take. So. Okay, so shall I start?
Yes.
Okay, so yesterday we constructed this Lagrange, which represent the generic effective field theory of inflation when there is only one degree of freedom involved. And we saw that there are two tadpoles, terms that are fixed by the background equations, and all the other coefficients are time-dependent free coefficients that are just determined by the different UV completion of the models. Different UV inflationary model just will end up in different values of this parameter for this Lagrange. All the effects of energy physics is encoded in these coefficients. We saw that it's very general, but as some people of you already asked yesterday, it's not very intuitive, this Lagrange. Where is the scalar field? Where is the inflaton field? As I mentioned yesterday, it turns out that this Lagrangian, as was just asked, has one less gauge symmetry than 4-dimensional diffs, which means that the graviton, the metric fluctuation, doesn't contain just the graviton, which has 2 degrees of freedom, but one more. And this one more is a scalar degrees of freedom. And the rotation in 3 dimensions will be the inflaton. So, in order to make this explicit, this means that it's possible to reintroduce the 4-dimensional diff for the diffs by introducing a Goldstone boson which we call pi for historical reasons, that nonlinearly realizes for the diffs. In other words, 4-dimensional diffs are not a symmetry, are not a gauge redundancy of this action. And since, as Nati said, Cyber said, gauge invariance is nothing, just a redundancy of the theory, they are so much nothing that I can always reintroduce a field pi that nonlinear such that I can introduce a gauge invariance in this theory by making four-dimensional gauge invariance. That is, I can introduce the tiny homomorphisms by making nonlinearizes. This is a manifestation that really gauge symmetry, especially when they're nonlinearized, are really nothing. Are just a useful way for us to write the actions, but not they don't have any physical significance. So we will do this. Because, but they are very useful because it makes the physics much more manifest and simple in some regimes. So let me just open a parenthesis and let me do a reminder of how this works for the standard model. SM means standard model. Okay. This technique is called the Stuckelberg trick. Stuckelberg trick. Now, the standard model, I mean, at least the gauge sector, LO energies, is described by the Lagrange of massive gauge boson. Let me just focus on that. So, if you take a non-abelian gauge theory, in the unitary gauge, it is. I mean, everywhere here I put the factors of 2 and minus is equal to 1. So then we have mu. This is the Lagrange for non-abelian gauge fields, where a mu is the trace, is a mu a times Ta, where Ta is the generator of some gauge group. Now, this Lagrange is not gauge invariant. We should never say that it's nothing to do with that. We shouldn't call them gauge boson. These are massive vector fields. Okay. In fact, you see that this is not gauge invariant. Just if you don't trust me, perform a gauge transformation. Which sends a mu into u a mu u dagger plus I over g u d mu u dagger, where u is a generic element of the group gauged, so it's e to the I Ta xa of x. Okay? So if I perform this transformation, S becomes integrand d for x. The first guy, trace of f mu square, was indeed gauge invariant, so we know the result is unchanged. Trace of f mu nu. But the mass term was not gauge invariant, so it will be transformed to m square over g square, trace of d mu, the covariant derivative, d mu u dagger, d mu u. You see that after the gauge transformation, the gauge parameter appears in the Lagrange is not gauge invariant, as expected. Now, and the part which is not gauge invariant is the one proportional to the mass. Now, gauge invariance can be restored or gauge redundancy can be reintroduced in a non-linearized way by saying that by exchanging u, which was e to the I Ta xa, to simply replace it everywhere there is Caa, I call it a field pi, so I put e to the I Ta pi a. So pi a now I say it's a field of the theory where pi a transforms where pi a now transforms under gauge symmetry e to the I Ta pi a tilde equal another gauge group transformation u tilde times applied to e to the I t a pi a old. So now transform, and this transformation is nonlinear. For example, if for U1, if the group was a U1 gauged, then this transformation, this u tilde is nothing but e to the I alpha of x, and means that pi tilde is equal to pi plus alpha. So you see that this is nonlinear transformation. 0 is not mapped into 0, so it's nonlinear. It's a very simple nonlinear transformation, but it's nonlinear. Because for linear transformation, 0 goes to 0. Now, okay. Now, once we're done this, now these guys now are a function of pi now. Just this, and now this Lagrangian is manifesting gauge invariance. This is because I assigned the transformation rule to pi to undo what is missing here. Now, if you Taylor expand, notice that so far I really have done nothing. I introduced a gauge redundancy by introducing a degree of freedom. But you will see why it is useful. It's just useful for the physical interpretation. So if you begin to Taylor expand, you can find that look at the pi terms. You will find that this term here will contain, for example, a kinetic term which is m square over g square d mu pi square. Plus there will be self-interactions of the which are pi square, d mu pi square. Let me drop all the a indexes. There will be some gauge group constants and so on and so forth. And then there are also mixing terms, because since these are covariant derivatives, there will be mixing terms between the gauge, the vector modes and the pi field. For example, you will get terms like m mu d mu pi. Okay, so now if you look at the pi Lagrangian, these pi terms, there are two things to notice. So there is pi is mixed with a mu by this term. However, sorry, maybe there are three things to notice. First of all, the pi is not canonically normalized. Three things. Pi is not canonical. Pi canonical is m over g pi. Then pi is mixed with this, and if you go to the canonical normalization, you find that d pi canonical square plus now I think is m. Sorry, this was m square over g. Sorry, yeah? And this becomes m a mu d mu pi. So canonical. You see, there was m square here, and then when g is killed by the covariant derivative. So we get m square over g, and then upon canonical normalization, I get this. So this is the mixing between pi and a mu is irrelevant with respect to the kinetic terms for energies much bigger than m. So this is the first point. Second point, and the third point is that there is a self-interaction which, upon canonical normalization, tells you that pi canonical square, there is an interaction which is pi canonical square d pi canonical square over m square over g square. Now, this is a dimension 6 operator, which implies that unitarity, there is a unitarity bound. Lambda unitarity is equal to m square over g square. So, putting these three things together, shows that there is a parametric large window for G much less than 1, for the gauge coupling much less than 1, there is an energy range between M much less than energy and much less than M over G, where pi is decoupled and self-interacting. And we large with perturbative but large self-interactions. So this means that if you are in this regime, up to mistakes of order up to corrections m square over e square much less than 1, I can simply describe the self-interaction of gauge boson, but that Lagrangian there. So instead of doing gauge boson scattering with the G mu nu, I mean, you're a formal guy, so maybe you're able to do that. These are complicated algebra. There is all the indices and so on and so forth. One simply does pi self-interactions with the quartic interaction and gets the same result up to small corrections. So this is called the Goldstone-Boson equivalent theorem. It tells us, I repeat it, that the scattering of whom this pi, what is the role? It plays the role of the part of the vector boson which was not gauge invariant. So it's the longitudinal polarization which is absent if the vectors are massless. And the longitudinal polarization can be described as a scalar degrees of freedom with the Lagrange over there up to these small corrections. And the description is not only simple because there are no indices, no gauge invariants, you don't just see gauge invariant, you just see it's a scalar field Lagrange. But on top of it, there are also many more physical properties are simpler. For example, you can see that unitarity, first of all, that you see that the theory of massive gauge boson is non-unitary, even though from here it doesn't look like so. It becomes strongly coupled at a scale which is m over g, and approaches violation of unitarity with a dimension 6 operator. Instead, if you do the calculation here, you find naively each diagram that, if you do the calculation here, there are these diagrams and also this diagram from the cubic self-interactions. Each of these two diagrams grows with energy as e to the fourth over lambda to the fourth. And the e to the fourth cancel to give you e square over m square. So you have to be very good to do the calculation, find the cancellation. Here you don't even need to do the calculation. So scalar fields are good, and in introducing the Goldstone boson, which was not necessary because this gauge symmetry is not present. So the gauge symmetry is just an artifact I'm introducing to why? To make my life simpler. Okay. Now, as you know, gravity is. Let's go back now to inflation. By the way, this is the Lagrangian that described the standard model until the 4th of July of 2012, when we discovered that the longitudinal polarization of the gauge boson is given by a true fundamental scalar field, the Higgs boson. Until 2012, this was completely fine to predict, to describe all the physics at energy scale below the Higgs mass. Okay, now gravity is nothing but is just the gauge theory, the theory with gauge redundancy given by diffs. At low energies, you can derive general relativity simply imposing this. And so we can construct, now, the Feti theory of inflation is nothing but the theory where four-dimensional diffs are spontaneously broken into independent spatial diffs, and we can therefore perform exactly the same trick to reintroduce the Goldstone boson. in the EFT of inflation. Okay, so let's do this. Okay, let me just follow our nose. It's exactly the same construction. The only difference is that it is the gauge group is slightly different, so we just exactly do the same things. So, for example, we will see that there were terms that were not gauge invariant. For example, let me just consider A of t a function like this, plus B of t G00. This is a typical representative of the terms we have. These are typical representatives of the terms that we have in the effective theory. So, okay, we perform the various steps. First, we perform a broken diff, t tilde equal t plus x0 of x tilde equal x. Now, G00 tilde, the new one, of x tilde of x is given by the usual law dx tilde 0 of x in dx alpha, dx tilde 0 of x in dx beta, g alpha beta of x of x tilde, I mean of x of x tilde. And therefore, if I plug back in the action here, becomes d for x square root of minus g tilde of x tilde times the Jacobian dx tilde and dx times so here I can just use the transformed fields. So instead of using g, I can write g as a function of g tilde, and I get under square root I get the determinant of the Jacobian. And then I use the old fields like this. Here I use simply this identity to express this field, the G field, in terms of the G tilde fields. And now I can change variables, change integration variables. From x to x tilde. You can... Oh, thank you very much. Good. I made it on purpose so that... just kidding. Yes, thank you. Perfect. And now we change integration variable to x tilde. You see that the Jacobian can simply be absorbed here. So the action becomes integrand d4 x tilde square root of minus g tilde of x tilde. And then there is a of t tilde plus x0 plus b of t tilde plus x0 times d of t tilde minus, just to open up what t tilde is, x tilde 0 is, in x tilde mu dt tilde minus x0 in x tilde mu g tilde mu. Sorry, here I forgot the tilde. G tilde mu. Now, you see that the action, even written in the tilde field, is not the one of before. I'm just repeating what we saw before for the gauge boson. It's identical. You see that the action is not the same because sometimes we're not gauge invariant, we're not diff invariant. G00 got this term, and all functions of time became functions of t plus x0. They were not gauge invariant, and we see that. Now, restore gauge invariance, restore time diffs. By saying that x0, I replace it with minus pi. Minus because it's good, it's just useful for us. Minus pi tilde of x tilde. And now if I do this, and I say that under diffs, so to save time, let me just replace it. Sorry, here there was minus. I mean, just to keep it consistent with here. I declare that under diffs pi tilde, pi transform in pi tilde of x tilde of x, which is pi of x minus c0 of x. You can see that this transformation is nonlinear. Again, 0 is not mapped into 0 and is quite nonlinear because there is a pi also inside the change of coordinates. So when you want to try to solve this is a very nonlinear function of pi. So after we do this, we can drop the tildes and conclude that we have an action which is the following form. Doing this directly for the action we care about, we get minus g. Notice that okay, let me just write it. So going back to the form Lagrange, we get m plus square r plus minus m plus square 3h square of t plus pi plus h dot of t plus pi plus, then there was the g00 term, m plus square h dot of t plus pi. So h, remember, is a function of time in general. Then I get d mu of t plus pi times d nu of t plus pi g mu nu. Okay, plus, for example, g00 square, which is m2 to the fourth t plus pi. Delta was delta g00 square, right? So it was g00 square plus 1. The background value g00 is minus 1. So the delta becomes simply d mu of t plus pi, d nu of t plus pi times g mu nu plus 1 square. And same for the other terms. Now, you can see what I've done. I have replaced c0 with pi, and since the tilde is just an integration variable, I simply drop the tilde. Now, you see that many terms now contains a pi. This pi is very important because now this Lagrange non-linearizes time diffeomorphism. And in fact, because pi transformed non-linearly to compensate the fact that some terms were not diffeomorphism invariant. For example, any function of time has become a function of t plus pi. G00 has become this block here. And you see manifestly it's gauge invariant because if I do t plus x0, pi goes pi minus x0 and x0 cancel. You see that, for example, these terms of square root of g, we don't have any pi because they were already diff invariant, like f mu nu square was gauge invariant in the gauge boson case. Okay, now, so why this is useful? As for gauge boson, as for massive spin 1 particle, the pi field, which is the Goston boson, the Goston field, is decouples from the gauge bosons, which in the case for gravity is G mu nu, at an energy scale much bigger than some mixing energy scale that we're going to estimate soon, and for energies much smaller than some unitarity bound of the theory that we're going to also explore. So when we are in this regime, then I can neglect all the metric fluctuations and I can just concentrate on a scalar field Lagrange. Very much here, to do scattering of gauge boson, we could just concentrate on the pi field, on the gauge boson. Now, okay, now we need to estimate the mixed scale. Now, to estimate the mixed scale is not super trivial because, contrary to the case of gauge boson, the theory is very non-relativistic and there are many scales in the problem. You can see, for example, by looking at the kinetic. So let's work for simplification in the limit where the time dependence of the functions is very, very small, so that these t plus pi terms are all this becomes pi fields by pulling out derivative of this time derivative of these functions. And let's assume that these functions are very, very slow, depending in time. You can see that this is an enhanced symmetry point because you can see that all pi's appear with a derivative apart when they are inside a function of time. So if you impose the theory to have a time invariant symmetry, it means that pi inherits a Schiff symmetry, which is therefore is relatively stable. So if we consider that the time dependence is very, very small, you can see the most important terms come from these terms here. And you can see that there are mixing terms. For example, you can see that there is a term that goes like m plus square h dot, which was the G00 tadpole, times d mu pi dot delta G00. So this is the mixing. And there is also a kinetic term, m plus square h dot d pi square, and this is the kinetic term. Now you can see, maybe I should have said also for the gauge boson, you can see that in the case of the gauge boson, the mixing was becoming irrelevant for the Ghoston boson at some energy scale, because the kinetic term has two derivatives, while this one has one derivative only, so it is one less derivative. So there exists an energy scale where that scale is bigger than that, that operator is bigger than the other one, the scale happens to be m. Here is similar. You can see that the mixing term has one less derivative than the kinetic term. So at some energy scale high enough, the method degrees of freedom, pi, decouples from the metric. This is nothing but the equivalence principle. It's a fancy way of saying that the equivalence principle that in the high energy limit, gravity is irrelevant, and we kind of live in like in Minkowski space. Maybe this is the modern version of the equivalence principle. Method breaks diffeomorphisms, but if you go to high energies, it's irrelevant. Okay, now, the problem we estimate in this energy scale is that the metric fluctuation is not an independent degree of freedom. So now, delta G00, we need to know how it scales delta G00. Delta G0 is a constraint variable. Very much like A0 in, for example, in gauge theories. That is determined by the metric. Like A0 solves a constraint equation. I don't remember very well, but something like Laplacian of A0 goes like the electric charge in the U1 theory. So you see that if you tell what the metal field do, which is the electric charge density, you know immediately at every time in every location the location of A0. That is A0 that solves a differential equation which doesn't involve time derivative. So is a constraint variable in terms of the metal field. This is why it's not an independent degree of freedom. In the U1 theory, you have four mu's. One is broken by four components. One is killed by the gauge invariant, set to 0 by the gauge invariant, and the other is killed by the fact that this gauge invariant imposes the one equation of motion for the components is a constrained equation. Now, similarly for delta G00, which is the gravitational potential, Newton potential, if you go to very, very short distances, is Newton potential. So it's also constrained. Because if it wasn't constrained, then this means that the metric would contain an independent degree of freedom, independent of the metric. But we know that the metric only contains spins 2 degrees of freedom, doesn't contain a scalar. So it solves the equations, which is a constrained equation. I mean, by opening up the Lagrange, you can find that the equation is takes this form, m plus square h delta G00, which comes from the expansion of m plus square, the Einstein-Hilbert term. And then there is the source, which just from the mixing term, you can see that it gives you this term here, so sort of this term here. And then you can solve it and find, at least at the level of scaling, you don't need to do any complicated algebra, but you find that the scaling tells you that delta G00 is h dot over h pi. So as advertised, this is a constraint equation, so it's just a function of pi. There is no initial condition not needed for delta G00. And then you find that pi is sourcing delta G00 without the derivative. So when we do mix the ratio of the mixing term over the kinetic term, they go like delta G00 over pi dot, which scales like h dot over h square, h dot over h, pi over pi dot. Now we are interested at energies of order Hubble. As I did in my first one lecture, you see that all the physics in inflation for the fluctuation is happening at the scales of order Hubble. So we evaluate this operator at energy scale of order Hubble, and this goes like h dot. So the dot omega goes like Hubble. So this goes like h dot over h square. So, sorry, or even before that, let me just say, is a dot over h times the energy, which is irrelevant, which is much less than 1, irrelevant for energy much less than h dot over h square times Hubble. Sorry, for energy way above h dot over h square times Hubble. This parameter is epsilon, so this is epsilon Hubble. So this is a very important result, because it shows, I should say that, first of all, what the equation of motion for delta G00 is determined by what is in the action. So for simplification here, I consider the case in which all these m's additional are 0, and I'm turning on only this term here. You can, right now, there is no other way to do it, as far as I know, that just at least estimating what are the equation of motion for the delta G00. So this is for M2, M3, dot equal to 0. But this is but now we find that in this case, the mixing scale for energy way above E mixing, which is epsilon times Hubble, which is therefore is much less than Hubble. The mixing between pi and G mu nu is negligible, is subleading, is small. And maybe if you're interested in effects that are present, even neglecting the mixing, this term can be neglected. Very much, this mixing scale is analogous to the M scale for the gauge boson theory. And what is very important for us is remember that we are interested in inflation we care of energies of order Hubble, which, for example, for this case, is much bigger than a mixing. And so, for example, for when these M2, M3 are all 0, this decoupling limit, it applies very well. This is the formal proof of why, in the first lecture, we could do all the calculation neglecting the metric fluctuation. Because if you include the metric fluctuation, you get epsilonic corrections, which, by definition of epsilon, are small. Okay.
So this stuff, if you did have extra structure inside
yes. Yeah, this is a mixing. Well, I mean, I'm not aware. Yeah, I'm not aware. When there's structure way inside the horizon, they're controlled really by the pi self-interaction. For example, this was a big confusion in the community when there was these resonance models. The people were solving all the constraints equation, We did this in 2 minutes because it's meta self-interaction. It doesn't come from gravity, right? So
Yeah, but I'm just saying this argument.
the mixing will work as well. Yeah.
But it wouldn't be point of argument.
No. Yeah. You have always to redo this argument, and you find what is the scale. That's the safe things. I can only underline that. And you find in the case that the mix is irrelevant as well. The idea is that if things happen at high energies, the metric doesn't matter. This Einstein intuition. Okay.
Yeah, so you say it's even better.
Yeah. Now, notice that this passage is a bit non-trivial because when we observe the CMB, we observe extremely low energy fluctuations. And why, therefore, we care only of energy scale of order Hubble during inflation, which is a very high energy scale? Because, as we showed in the first lecture, when we compute the fluctuation at energy scales of order Hubble, we can convert to the zeta variable, which is then constant forever. No matter how to low energies it goes, no matter how stretched it is still constant. So, for our purposes, if we can compute things at Hubble, we are done. And at Hubble, the mixing scale is small, and then we can do it. Now, there are some models. For example, if I turn on some of the other operators, the mixing scale will come up, and sometimes the mixing scale becomes above the Hubble. In this case, the decoupling limit does not apply, and this simply means that one has to come back to the action we wrote before, the full action, and just or even the current action, and not neglect the metric fluctuations. So, life is not always nice, but okay, it's not a tragedy. So the action applies always, but this simplification limit applies very often, but not always. Now, it turns out that this mixing scale is true also when we turn on M2, M3. It just begins to be modified when we turn on the strict curvature terms that I've wrote in the flash backboard. So, if in this case, for energies much bigger than the mixed energies, as we can just focus on the pi action, which takes the form of d4x square root of minus g minus m plus square h dot d pi square d mu pi square plus m2 to the fourth pi dot square plus pi dot cube plus pi dot square d pi to square plus d pi to the fourth plus m3 to the fourth pi dot cube plus pi dot d pi square pi dot square d pi square plus pi dot d pi to the I think d pi to the fourth. Now this is simple. Okay, now this is simple. So we have reduced all that complicated action with metric fluctuations, so on and so forth. We just showed that to compute observable in inflation, there are regimes in which the observable are controlled by this Lagrange, which is a scalar field Lagrange, very easy to deal. I mean, maybe you like very hard calculation, but it's always better to have an easy calculation to do. So this is very easy, in particular if you consider how general is this action, right? We didn't even assume that there is a fundamental scalar field. There is it's super general and also super simple. It's not super symmetric. But sorry. Yeah. Now you can see that. Let me open it up a bit. Now you can see that there is a standard kinetic term, a relativistic kinetic term. Okay, let me just say, there is a relativistic kinetic term here. This term is already Lorentz invariance on its own, and you see, in fact, it's quadratic. It doesn't need any term. However, for example, this term here, this contains a kinetic term, pi dot square, it's a kinetic term, but there is no space kinetic term. So this term is non Lorentz invariant. But non Lorentz invariance or tiny homomorphism are just non-linearly realized, and this means that this term must come with some nonlinear term. In fact, this term comes with this, and also with this, and so on and so forth. Similarly here, there is a cubic self-interaction, This operator starts with a cubic self-interaction, which, however, is not Lorentz invariance. And Lorentz invariance is restored by adding the following term. So terms come as operators are blocks. No, fluctuations come in blocks. So, in particular, for example, this term implies this means a relationship between observables. Relations between different observables. For example, you can easily imagine that if I have a pi dot cube interaction, I will have a three-point function non-zero in the fluctuations. And this means that if I have this three-point function induced by this operator, I must have also a four-point function induced by this operator and a five-point function induced by this operator. So there is a whole series of observables that are just cascading just because of symmetry. Okay, so now let me just summarize a bit. So as I said, this is the Lagrangian for the fluctuations of all the inflationary model. It has several limits. We're going to explore them very soon. There is, if the mixed scale is very small, there is an extremely simple limit. And since it uses, as all effective theories, symmetries in the most strong way possible, we use them in the most possible way. For example, I just mentioned connection between observable. This is very non-trivial, that the three-point function is connected to the four-point function and five-point function. Similarly, you can see that, for example, the spatial kinetic term here is absent in these terms. This means that the space kinetic term has a prefactor which is h dot m plus square times di pi square. So its sign is determined by the sign of h dot. Now, you know that in FRW, if the sign of h dot is positive, it implies a violation of an energy condition. In this case, the sign of this term is the wrong sign kinetic term, which means that the kinetic energy, the gradient energy, the spatial gradient energy of the Gaussian boson would be negative, and so it will signal instability. This is not a mechanistic instability. This is a Gauss-like stability. It's a stability as large as the fastest gradient you have in the theory, which is the cutoff of the theory. So it's a disastrous instability. So this is why violating the energy condition in the field theory is very hard. It just, you see in the ice. While, for example, when this theory was developed, people were always trying to evaluate the energy condition, find always some obstacle. This is just makes manifest immediately the obstacle, and also tells you how it can be fixed. It can be fixed by adding the extrinsic curve to terms. However, the terms pi dot square is not fixed. The prefactor is h dot m plus square plus m2 to the fourth, which implies that the pi dot square can be made positive even for h dot positive by choosing m2 to the fourth negative. But this at the cost of making the fluctuation in pi, and the fluctuation pi go at a speed which is different from 1, because the prefactor of CS is different. The prefactor of pi dot is different from the prefactor of the pi, so the dispeciation will be of this form, which is not a problem because the theory is not relativistic. CS equal 1 was not protected by any symmetry. But as we see, the moment we turn on this operator, we turn on also these other interactions, and so we will generate self-interaction, which ultimately give us non-Gaussianity. It's also another advantage of this approach, I would like to stress, is the fact that the fluctuations are truly fluctuations. If we were to work with a scalar, as we mentioned yesterday in several occasions, if you have in inflation, if you have an operator like this, it contributes to the quadratic Lagrangian by putting 8 legs on the background, and one gets this. So in general, it's very hard to determine to assess the importance of an operator around how much an operator will be important around the de Sitter solution from the background solution, from the Minkowski solution, because of this effect. And as you've seen in cyber lectures, physics can change a lot as we change energy scales. Instead here, each operator contributes only at finite order, at the manifest order in perturbation theory. This is a cubic, this is a quadratic, and that's it. Okay, now, I think before proceeding, I think now this is time to do a rigorous calculation. So far, I would like to, I'm proud, we never did any calculation, okay, in this theory. But I think it's important to show that actually now one can do precisely the calculations, because now also the level of accuracy of the experimental observation is such that cosmology, we are doing percent calculation. It's not enough any longer to do squiggles. So for this reason, I think I want to show you how to do a rigorous calculation. And this is also to explain how to quantize a theory when there are these metric fluctuations. So how to make field theory in, more generally, how to make field theory in a FRW space or the zeta space, in an accelerating space-time anyway. So right now I said that to get the mixing scale is so small that one can get all the interesting results from just concentrating on the pi Lagrange, the decoupled Lagrange, which is what we did essentially in the first lecture. Remember, I told you, oh, let's forget the metric fluctuation, let's just focus on delta phi, and this was the reason. But now let's verify this explicitly with calculation. Okay, let's ignore that point, suppose we don't know it, and keep metric fluctuations. So now we're going to compute rigorously the 2-point function. Of zeta, starting from pi. So the same thing we did in the first lecture, now we do it carefully. Now, first of all, we have to parameterize the metric. And it's very useful to use the ADM decomposition. So we get minus n square dt square plus hij dxi plus ni dt dxj plus nj dt. So this is the metric, which we assume is close to FRW with small fluctuation. So, and then the action in ADM becomes ADM action, takes the following form. Okay, again, in the notes there are all the factors of 2, and so here I'll neglect them, even though we do the calculation, but the factors just carry on. So the Einstein-Hilbert term becomes the lapse function times the Ricci scalar of the three-dimensional service. Then there are extrinsic curvature terms. This is the extrinsic curvature kappa I defined times n, so it's just the same. Index are lower arrays with hij, which is the induced metric on the spatial slicings. And then there are the EFT terms. So this is m plus square r4 plus, now there is the various terms, m plus square h dot of t plus pi times 1 over n 1 plus pi dot square plus 2 over n 1 plus pi dot ni di pi minus n hij di pi dj pi minus 1 over n ni di pi plus all the other terms. So hij explicitly is given by dt of hij plus the covariant derivative respect to the metric h and j symmetrized. Now, so we write the arithmetic in this form. The action in this form.
So in your notes it says NIDI pi squared for the last term.
Okay, thanks. I'm just copy the formula. Yeah. I think. Okay. No. Thanks. I mean. The next step, this is the theory gets quantized like so. Now we quantize the theory, and this is done as for all gauge theories. Okay, this is now a gauge theory, so it's quantized as for all gauge theories. So, for example, I like the way it's explained in Weinberg book in the volume 2, for example. So nothing fancier than that. So now, you follow the textbook. This means that you take the equation of motion, with respect to the constraint variable. So with respect to delta G mu nu. Now, the two most relevant equations of motion are the one which are associated with the constraint variables, so which are n and ni. So this parameterization in ADM parameterization is useful because it turns out that n and ni are automatically constraint variables. Now the equation of motion for n and ni are something like this, grad I, so delta S in delta ni, which we set to 0 by the equation of, okay, delta S in delta ni is equal to grad I of n inverse Eij minus delta ij e plus 2 over n h dot of t plus pi times 1 plus pi dot di pi plus minus nj di dj pi di pi, and then this must be equal to 0. So this is the equation for respect to nj. Now, sorry, before set it to 0, okay, and then there is an analogous equation for respect to n equal something. What you see is that in this equation, n and nj appear without time derivatives, and the same for here, very much like delta g00 appeared in the squiggly equation without time derivative upstairs there. So this means that we can solve without loss of generality, solve for n and ni. So this means that, okay, we can solve for n and ni by making delta S in delta n equal 0, delta S delta ni equal 0. And before doing that, this equation can be solved only if you fix the gauge. So now that we derive the equation of motion, we can fix the gauge. So the gauge we choose is okay, first the fix the gauge, let me check the degrees of freedom. Let's count the degrees of freedom. So the action has G mu nu, which has 10 components, from G mu nu plus pi, which are 1. So we start with 11. But then there are, you can see that the n and ni. So first of all, I can fix the gauge. And the gauge, I have 4 degrees of gauge symmetries, because also time diffeomorphism is restored. So I have 4. I can kill 4 variable by the gauge gauge invariant, gauge redundancy. And then you can see that 4 variables, n and ni, are actually known in terms of the other variables because of the constraints equation. So I get -4. And I get 3, which can be written as 2 plus 1. These are the two helicity 2, the helicity 2 state, and this is the scalar. So this actually indeed contains 3 degrees of freedom as advertised. So more explicitly, let's we fix the gauge. And the gauge we choose we choose the special metric to be a square delta ij. You can call this a specially flat gauge, or pi gauge if you want. Okay, once you have fixed the gauge, you can solve these equations for n and ni, and a linear level. Now, we're going to be interested only in the quadratic Lagrange, which it's easy to convince yourself that you require only the linear solutions for these terms, the linear in the fluctuation. So at the linear level, there is an accidental fact that really, also for the cubic action, one can solve the constraints equation only linear level in the fluctuations. But we'll not go over that. And we will find that n is 1 plus h dot over h pi, and the di and I is equal to h dot over h square dt of h pi. So you can see that this, as advertised, that once pi is known, which is the method field, these two metric fluctuations are completely known. And also you see that these are excited by pi without any derivative. Also here the derivative cancel, which means that in the energy limit they are irrelevant, as already advertised. Now plug back the solutions in action, and do the algebra. Now we are not interested here in tensor mode. We are only interested in the pi. So we'll just focus on pi. Okay, after a little bit of algebra, you find that S is given by the integrand d for x, a cube, h dot n plus square, pi dot square, minus 1 over a square di pi square, plus epsilon 3h dot, or epsilon h square, pi square. So this is the pi action after solving for the constraint equation. So by automatically highlighting the only unconstrained degrees of freedom in the theory, scalar, and you can see that it's very similar to what we got here. I mean, the factors of 2, 3 are just there because I neglect them. So these actions are identical to what I get, ignoring from the beginning the fluctuations, apart from this term here. So the mixing with gravity gave me a term which looks like a mass for this Goston boson. And you can see that it's very, very small. It's down by epsilon. So this is relevant only at energies of order epsilon h square, as advertised. Okay, once I have pi, I remind we want to compute zeta. We ultimately want zeta. And to do that, we say that we remind you that zeta can be found by performing zeta can be expressed as function of pi by the following thing. Zeta is defined in gauge as the scalar degrees of freedom where pi has been set to 0. by gauge transformation. This we can do with delta t transformation because pi goes into pi plus delta t. And as advertised in this gauge, the metric hij in zeta gauge goes like a square e to the 2 zeta. So in order to express zeta in terms of pi, one can simply perform a time diffeomorphism equal to minus pi, so that in the new gauge pi is equal to 0, and zeta, therefore, a linear level is equal to minus h pi. This is also quite intuitive, because with pi, you see, pi is the Ghost-on boson time translation. Pi represents the fluctuation of time. Pi is the time delay that was introduced, is the rigorous way of thinking about the time delay that was introduced in the first lecture. And then you can see that zeta was basically delta A over A due to the delta t. And in the first lecture we said that it was h delta t. You can see that pi, I forgot to say, but pi is unity of time because it was always appear as this. Represent the fluctuation of time associated to the infrared fluctuation. And then the zeta is nothing but the fluctuation times the rate of expansion of the universe, which give you delta A over A, which you can see here. Zeta linear level is nothing but delta A over A. So if you can compute pi, we can compute zeta. Okay, now we solve for, we quantize. Now that we have isolated the degrees of freedom, we can forget about, there is nothing fancy about gauge symmetry or gauge redundancy because, again, it was just a redundancy. So now we have the action here, which has an action with no gauge invariance. All the gauge symmetry has been fixed. There is no gauge redundancy. There is one unconstrained degrees of freedom. So we solve it like an unconstrained scalar. So we do pi. So, and even if it lives in an unperturbed FRW space, so it lives in a curved space-time. So the momentum conjugate to pi, maybe let me call it p. P of pi, which is delta L in delta pi dot, is of order minus m plus square h dot pi dot. And then we impose that pi, p of pi, is equal to I. Okay? These conditions are satisfied. This is satisfied. If we impose that the operator pi, just for here, just for put the hat just for explicitly, or let me just pi is equal to pi ok classical times a of t times a dagger of k plus pi of minus k classical of t pi of k star times a of minus k. So I expand the field as an harmonic oscillator, where this pi here, this wave function here, satisfies the equation of motion, the classical equation of motion. Pi classical is such that 0 is equal to delta L in delta pi, which for our case is, roughly speaking, d in dt of minus a cube h dot m plus square times pi dot plus h dot a k square, the gradient term, pi of k. And this is for the classical. Okay, now we need to solve this differential equation. So we define the vacuum, as obvious from this writing, define the free theory vacuum 0 as such that is annihilated by the annihilation operator. But this statement doesn't say much until we say how we solve this equation of motion, which is a second order differential equation, and so requires two initial conditions. Okay? There is a very physical way to impose these initial conditions. So in the limit, which is exactly what we did in the first lecture, in the limit k over a much bigger than Hubble, which means very early times, the fluctuations are way inside the horizon. And by the equivalence principle of Einstein, we expect them to be the same. The solution should be the same as what is in Minkowski space. So we impose that now going to conformal time, eta, where d eta times a is equal to dt, then a is 1, a during inflation, the theta space is minus 1 over h eta. Eta goes from minus infinity to 0. So k over a is becomes k eta. In the limit k eta minus k eta much bigger than 1, so very, very early times, way inside the horizon, the fluctuation should approach what it is in Minkowski space, which is, roughly speaking, 1 over k to the 1/2. But it's not just 1 over k to the 1/2, because it's not just that, because there are all the factors. First of all, the frequency is k over a. That's the physical frequency, so it should be k over a to the 1/2. And then there are a bunch of factors that come from the canonical normalization of the scalar field at early times. This is not a canonical normalized scalar field. Even at early time where a can be considered constant, there is this factor here, which can be written as, apart from the factor of 2 and so on that you can find in the notes, is roughly speaking epsilon to the 1/2 and Planck. And then this will go e to the I k eta. Notice that k eta is basically k over a times a eta, which is, roughly speaking, k physical times t. So this imposes, we need to solve this equation with this boundary condition at early times. Now the solution reads. Now the solution is a bit non-trivial to find, because for a generic time dependence of h, these are it's generic function of time, and this differential equation we cannot solve. However, there is an important simplification that we immediately realized. We can immediately realize that we need to do the calculation only up to Hubble crossing, as we did in the first lecture. Because as soon as the fluctuation cross Hubble, we can write zeta as equal to minus h pi, and then the fluctuation is constant. This is good because it wouldn't be, even though h dot has a small time dependence, if you were to use this differential equation for a very long time, it would break. The approximation considered h dot constant, which is the first approximation if the variation is small, breaks a very long time. Luckily, we need the solution to this differential equation only for an Hubble time around Hubble crossing, because when the field cross Hubble, there is this variable which is completely conserved. So this means that we can solve with Leonardo parameters set to 0, solve at leading order in Leonardo. In slow roll, and the solution reads pi classical of k is equal to minus 1 over, apart from factors of 2, epsilon to the 1/2 and Planck 1 over k to the 3/2, and then there is 1 minus I k eta e to the I k eta, and now zeta again, zeta we expand it as a zeta classical A plus Hermitian conjugate. Zeta classical a dagger of k here, and zeta classical is nothing but minus h pi classical, so we know it. And this means that zeta of k t zeta of k prime t prime is nothing but a square pi classical pi of k pi of k classical of t pi classical star of k t prime delta 3 of k plus k prime, and for late time k eta goes to 0 when the mode is way outside the horizon. The solution reads 1 over k cube h to the fourth over 4 minus h dot n plus square. And in this approximation, these are all evaluated, they depend naively on time, and so slightly on k by the fact that these are evaluated at t equal t freeze out, which depends on logarithmically on k. And if you look at the notes, the 4, you get even the 4. So this is the same result as we obtained in the first lecture, but fully in a completely rigorous way, and you achieve also to get the factor of 4. So this is the computation of the 2-point function of the inflator fluctuation, which is so far the only thing that we have measured experimentally. So this computation is all what we need to match all of cosmological observations from inflation. All the rest comes from plasma physics at the time of recombination, or from the gravitational collapse of galaxies, and so on and so forth. Now, there is another way to do the calculation. I'll just add one comment. You can see that this calculation was relatively easy, because first of all, because we knew from the beginning that we could have just forgot about the metric fluctuations. But here I wanted to teach how to do the quantization with the metric fluctuation in. It's not a tragedy. One has to work a bit. But one finds that the metric fluctuations are indeed very, very small. One could have done a calculation in a different gauge. You might say, oh, but I wanted to compute zeta ultimately, which is a good variable in the infrared where fluctuations are constant. To go to zeta, one would have to go to a gauge where pi is equal to 0. And this is called the unitary gauge. Unitary gauges are very well known to be very good in the infrared, but infamously known for being very bad to highlight what is the right degrees of freedom and the most important terms. If you were to do, and in the note it's written, directly the calculation. So when we get to this point in the calculation, when we were writing n and I, we could have chosen, and we could do the calculation in a different gauge, set pi to 0 and work directly with zeta. You will find that at that point, the contribution of the metric fluctuation is all what you have. That is, all the scalar field emerges directly from the metric fluctuation in an incredibly non-transparent way. For example, it's very unclear why delta G00 gives rise to a kinetic term for a scalar degrees of freedom unless you put pi, because otherwise, if you do in zeta gauge, delta G00 in zeta gauge is nothing but 1 over n. And this becomes the kinetic term for the fluctuation only thanks to the solution to the constraint equation. So it's very, very mysterious, and this is also why this calculation for a long time were considered difficult. But the general lesson is that the relevant when the gauge symmetry are broken, it's always good at least in high energies to go in a gauge where the Goldstone boson is manifest. This is a law that applies everywhere in physics that I know. Now, next class, we will quickly skim over some, we will make an additional comments on the effective theory of inflation, talk about some different limits. Here I focus on roll inflation. I will see that as we turn on other operators, we get different inflationary models. I will briefly go through the Lagrange and mentioning the issue like technical naturalness and so on and so forth. And then we will compute with something which is, I think is more interesting. We'll talk about the correction to the quadratic Lagrange which give rise to the non-Gaussianity. And then we'll end. Okay, thanks. Yeah, questions? Yeah, questions? Yes.
Is there the idea of the field displacement, is that here, or is it going to go like a Transplanckian field displacement view?
Yeah, you can think of it as the fact that if you have a Transplanckian field range, is the fact that the integral of I think in some sense it's gone, but you can think I think the remnant is the fact that the integral in time of h dot of pi during the de Sitter epoch is quite large, and this is associated to the canonical normalization of this field. If as soon as one tries to make B modes very large, this h dot also is pushed to be large, and one can see that this you can define a quantity here, which is sort of the integral. I mean, a sort of the integral of pi canonical of Remplanck. This is mapped into the integral, a sort of delta pi canonical, how much pi canonical changes during inflation, which is proportional to the time duration of inflation of Remplanck, and this becomes large. So you can reconstruct in this way, though it's it's more hidden, but because I think because that Transplanckian range is really, I think it's more like an energy constraint. It's a constraint on the energy UV completion of the theory. From the fatty theory, it's okay. From this, now, you might wonder more like one could wonder more about mass terms here, but as I'll mention next class, actually these mass terms are very naturally suppressed by Schiff symmetry. So from the fatty theory, one can impose a Schiff symmetry and see no issues with Transplanckian physics. The reason why some string people is not so happy about this is because it's not trivial to get Schiff symmetries in string theory, and other people will talk about this. So that's, but from the Rengel point of view, it's not an issue. Other questions?
So, okay, so you interpret this theorem as the fluctuation in the time coordinate essentially, so that you should, so, but like some people use like this Bardeen potential, the return gauge invariant of the get-go, and then basically, so this would be equivalent to doing the quantization in the conformal Newtonian game, for example, and if you choose pi equals to 0, it would be the isochronous or synchronous game.
Yeah, so when I mentioned that the theory was very complicated, the way it's explained, I was very polite. I think that way is super complicated. Yeah, so I don't know. If you're able to understand that review, please let me know. I wasn't able to understand. Yeah, so first of all, calling phi Bardeen potential gauge invariant potential is an extremely confusing, I would say even wrong way of calling it. Because the gauge invariant phi Bardeen is nothing but phi in Newtonian gauge. Of course, when I go to a gauge, okay, it's gauge invariant. Then we can write it as phi Newtonian can be written in all the other gauges. It just just basically one just does a calculation in one gauge. Even my calculation is not done with phi Bardeen, is also gauge invariant. So that's a first confusion. But I think the standard approach, in other words, this calculation can be done in many gauges. Synchronous gauge, which doesn't completely fix the gauge, so it's not much use. But one could use something called Newtonian gauge. I think by now, really people uses two gauges, really. The pi gauge, the specially flat gauge, or the zeta gauge, which often is called Maldacena gauge, so usually it's good. And because at least, but it's not so good, but it's very good in the infrared. It's very good in infrared, but it's very bad to highlight the relevant degrees of freedom. People, since the early 2000s, began to specialize on these gauges. And but as I said, you can do the calculation the gauge you want. If the standard way of doing it goes all the way of solving the constraint, plug it back, and it's a miracle that it looks now there is a scalar field of freedom inside. They don't even tell you that there is a scalar when you start. Instead, you see, with pi gauge, I would say it's kind of obvious.
Right. Yeah, it's trying to start the map.
Yeah, the map is that they do the calculation in a different gauge, and then you can write zeta. Ultimately, everybody needs to compute zeta, and zeta is something like phi h minus psi h dot h. I don't something I found totally mysterious. It's often called Monkhonov Sasaki variable. I don't know. I mean, but this was it was very complicated to compute these things in the early 90s or late 80s. So this was a remarkable achievement that this formally was very good to establish, oh, look, we can do the calculation, we are right, no problem. At the beginning, people was even doing, in the 80s, oh, let me squiggle with delta t, for example. It must be this. People was even very big people, was even got it wrong and say that delta rho over rho of inflation was proportional to v prime delta phi, okay? So there was a lot of confusion, okay? Which, as I highlighted, this is completely wrong, okay? So it was very good to establish. Now that it's established, we try to simplify it. So okay. So there is no need to learn it in the old way, I think. Yes?
You set epsilon to 0, so you're just sure of the potential of the scalar field is purely constant. Seems like a lot of things diverge.
Yes. So maybe you skip the passage. That is, but you didn't say that. If you set v to 0, epsilon, naively you think that you're approaching the Sitte space, where the canonical normalization of the scalar field goes to 0. I thought this is what you meant. Yeah. Now, in fact, the de Sitter limit is very complicated for inflationary theories, but these kinetic terms go to 0, but there are other operators that I wrote down, the one involving the extrinsic curvature, or delta G00 square, that do not vanish in the de Sitter limit. So the de Sitter limit, as I will mention next class, can be done in several limits. This limit is kind of slightly sick, which means that the theory will become eternally inflating. But there are other limits where the theory is well behaved. The fluctuation is still small, and one achieves the Sitter space. But they are very different models in the UV. Thanks. Okay. I think.